a recording, so please don't make it awkward. And that's going. All right, so lesson 9 is going to be open shortly, and we get access to loops. Okay, loops are fantastic. They are on the short list of super critical programming concepts, along with functions and things that we haven't gotten to yet, but we're getting those super important things as we go. Okay, let's go like this. Sorry, not computer audio. Continue. Stay co-host. All right, go ahead and can you turn off your screen, please? No, not you. Can you turn off your screen? Thank you. And let's face this way. Folks, this is where the first 10 minutes is happening. So go ahead and turn around. Fantastic. Okay, if you're watching on the replay, which is not any of you, we are going to watch the video from Bubble 2, but it's not going to work well on the replay, so you can just watch it on your own. And for people in class, we're going to go and watch. This should work. All right. Loops and sound.
My name is Jerome Holman, and I work in the Windows Devices group at Microsoft. It's basically a team where we build cool stuff, tablets, phones, things like HoloLens that hopefully will excite and delight customers. Computers are not infinitely fast. They are much faster than human beings at many tasks. In 2014, the fastest computer in the world was clocked in at an astounding 33 quadrillion calculations per second. Now, for some tasks like composing a song, we generally think human beings still do a better job. For highly repetitive tasks that can be automated, computers are much, much better. Programming languages usually have a few different ways to define and control behavior that should repeat. These are usually called loops. They go by different names in different languages like for loop, while loop, do while loop, for each loop, repeat loop, and so on and so forth. These types of loops have small differences, but all of them are just different ways to get the computer to execute some lines of code repeatedly. The generic term for looping is iteration. Iteration is just a fancy word that means repeat. It usually is in reference to the repetition of a process or a procedure. This is why iteration is a good generic term. Often in programming, we have an algorithm that just needs to repeat a specific number of times, or repeated while some condition holds true. We're going to show you how to use a looping structure called a for loop in JavaScript. You can find for loops in the control section of the toolbox. It looks like this when you drag it out. A for loop in JavaScript, like this one, is just a type of counter loop. It counts up from 0 to the number you type in. Why does this simple for loop look so complicated? JavaScript, unlike some languages, doesn't provide a simple repeat loop structure. The for loop is a very powerful and versatile looping structure for both advanced and simple tasks. We're just keeping it simple for now. Let's do a little experimentation. You can drag any commands you like inside the for loop block. These commands will be executed over and over for however many times you specify in the loop. When you run the loop, notice the app lab highlights each line as it executes. Now, why does the for loop block highlight after each iteration of the loop? That's because the for loop needs to check its counter every time to see if it should stop or run the commands inside the loop one more time. Well, that's not terribly exciting, but it's because we're not really using the computing power that looping gives us. Instead of looping this piece of code 4 times, let's loop it, 200 times and see what happens. Now that's more interesting. One thing to note about loops is that your code will still execute from top to bottom as before. You can put lines of code before the loop if you need to get something set up before the loop starts. Likewise, After the loop is done executing, it will pick up on the line right after the loop. For example, if you want to move the turtle before drawing this figure, I could use a move to command before the loop. And if I want to draw a red dot to see where the turtle ends up, I could add lines after the loop. You will use the same top-down design in many of your projects. These problem-solving techniques will help you identify where loops belong in your code. You still might want to write a function to do a small part of your program, and then write a loop to call that function. Take, for example, the problem of trying to draw this. You might recognize that this is just a bunch of squares, each one rotated slightly before being drawn. Previously, we would have had to make a function to draw a square. To get the 10 rotating squares, we would have had to call this function 10 times, turning a little each time after we called the function. This would have involved a lot of copying and pasting. This code works, it does, but it's very repetitive. Let's just see if we can simplify our code with a loop. We already have a working function that does a piece of the problem once. We can easily stick the function call into a loop and do it multiple times. Clarity and readability are important considerations when programming. As we can see, this code is now much more readable. It's obvious just from looking at the loop that the intent is to draw a square a bunch of times. Loops are a powerful programming construct that uses the computer's primary advantage over humans, that being their amazing speed. By repeating commands as many times as we wish, loops allow us to solve new problems at a scale that would be impossible without computers. There is still much to learn about the loop, but the concept is simple. Loops repeat commands as many times as we need. Now you know how to use a simple loop. You can use them in your programs and take advantage of your computer's power and speed.
Okie dokie. So let me go ahead. All right, go ahead to lesson 9 and jump in at bubble 3. And let's do some loops. I'll put it on the back here in a second. There we go. All right, so you will see that we now have a folks, hold up a second. You'll see that we now have a toolbox category called control, and there is our for loop. All you need to know at this point is that the number of times you want to do something goes in the only available blank. Okay. Later on, we will talk about what is actually happening here, where we're declaring a local variable. We're saying how many times we want to do it and how much that counting variable should increase each time. But don't worry about it. For now, the only thing we can change is the number of times we do something. And all we need to do here is run some sort of loop. It doesn't say specifically what we need to do, but copying the, does it say specifically? Yeah, so move forwards and turn 137. So let's do a move forward. It has it at 25, but it's kind of hard to see. And then we need to turn left 137. And how many times do we want to do it? Let's see. It's probably says, wow, that's slow. Okay. And to say how many times we should loop, I'm not terribly concerned, so long as you get something that works. And that's all it needs to do. Okay. The components are the loop, and then everything you want to do goes inside of it and in order. Okay. the order that this is called is what's going to get called every time through the loop. Bubble 4. Second. So, bubble 4, we have a supposedly working function called draw square, and it receives a parameter called size that's used as the value for the move forward. So that means when we call it, we need to give it a value to send to that parameter to pass through. But what we want to do is call it a whole bunch of times. All right. And so we have a loop. We need to then call our function. The function is named draw square. And we need to send it a parameter. We need to send it a value to be received by the parameter. How big do we want our square? Nothing wrong with 100. And we want, let's say how many we want. A whole bunch. 72. Okay, so if we just did that, move forward 172, it's just going to draw 72 squares on top of each other. We need the slight turn, I guess turn right in order to copy it. And I don't know, 10 degrees. It's probably, what's 72 divided by 260? Whichever. And there we go. We're drawing squares with slight changes each time. If you speed the speed selector all the way up, it kind of happens instantly. But you'll see when we get into complex things, you actually see it running. Okay. So that's it. We have a loop running right away. It's not in a function definition. It makes a call to draw a square, sending it a value, and then turns right 10 degrees, and then does it over again 72 times. What's up? There's computer, there's computer, there's computer, there's computer, there's computer. I didn't turn it black if that's what you're asking. Okay, bubble 5. So bubble 5 is a quick check for understanding situation, and it's asking what's happening here. Describe what this code does. We've seen all these blocks before. The pen color and the move to and the dot size and the loop. Like these 1 to 2 sentences doesn't mean it has to be a super complex response with like commas and stuff. Simple sentences is fine. Just say what it does. I'll give you a hint. It does 4 things. Well, does 3 things a bunch of times, but the bunch of times is the 4th thing. I'll give you another minute on this one. Let's see who has even clicked one thing today. All right, let's go to bubble 6, which not coincidentally is that chunk of code. That very chunk of code. Wow, it looks like almost everyone is participating today. That's good. Okay, so this is that chunk of code from before. Okay, you can see what it does. It has a loop. 100 times it will do the following. It sets the pen to a fully random color, full range of redness, 0 to 255. full range of greenness, range of blueness, but half opacity. It goes to a random location using the full screen because 0 to 320, okay, move to the first number that you give it is the X, the second number is the Y. For the X, we have a full range of 0 to 320, which means anywhere left to right, because X is the distance from the left. So 0 from the left is the left, 320 from the left is the right. So full range left to right. And the Y value, 0 to 450, is the full range of height because Y0 is the top edge. And for us, Y450 is the bottom edge. So this means anywhere on the screen, which will be relevant later when we do something else, and makes a dot of a size between 1 and 20. That's what it does. That's what the last one does. And if you said that, you were right. Okay. For this one, our goal is to just increase the number of loops so that the screen is usually filled up, which is a weird challenge that has some sort of usually as the criteria. Somewhere in the low thousands, I think, is the number of times that it takes to cover the screen. And whatever works is fine. Bubble 7, we get the same thing. Except our goal here is to do it again, except cover up the screen. So we have this loop that is picking a random number, moving to a random location, and making a dot of a color. We want it to do the same thing again, except instead of a random RGB, we want it to be white, which white is 255, 255, 255, which I don't expect you to memorize all of the RGB triplets or a bunch of them. You do need to know that white is 255, 255, 255. Black is 0, 0, 0. And then red, green, and blue are maxed out in their respective categories. So if we have a white pen and then random location, random dot size for the same number of times, it almost covers it up. I don't know, 4,000 might be enough. But either way, you'll notice that even if you have the slider all the way up to rabbit, you can still sort of see stuff happen. And the reason for that is that it's doing a ton of iterations. Okay, all the way to the right should happen instantly, but you can see that it is a little slow. But also you can see that it runs in order. It does our colorful dots first, and then our white dots afterwards, which is the point of this one. And cruising right along. Okay, Bubble 8. Bubble 8 is going to be the project for the rest of the way. Just like last time when we did Under the Sea, this is Under the Sea again, but it has other features, and we are going to extend these other features with, so you know where we're headed. This is our goal. Okay, you can see we have 5 different components if you look closely. The 3 we're familiar with, the fish, sea star, and seagrass. But there's the sunbeam, and there is a bubble. So there are 5 components. And right now we have 1 of each. We are going to make a bunch of each with loops. Super easy. For Bubble 8, all we need to do is take a look at the code, which, folks, you'll want to listen up, even if you are meeting the criteria and moving along in the lesson. I love the enthusiasm, but there are tidbits you're going to get here in the next couple minutes that you're going to use in the next lesson, which is a project, which will probably be 2 class periods because I want it to be good. You're going to create in the next lesson, not today, your own sort of digital scene in this vein that has several components. Okay, several multi sort of tiered components. So if we look through the code, we have it starts out with hiding the cursor, which is fine, and pen up so that it can do some moving. And then it has 6 function calls, which are just starting the things in whichever order. And they all call to the draw all set of functions, draw all seagrass, draw all sea stars, draw all fish, draw all bubbles, and draw all sunbeams. Each one of these makes a call to its lower level function, draw sea star, draw seagrass, draw fish, draw bubble, draw sunbeam. Okay, this is the abstraction. We can play around with the function, the higher level calls to get all of our fish the way we want them, but we never have to worry about the draw fish function because it works. Okay, this is something you're going to have to deal with next time, where you come up with your scene, which I'll give you some examples so you're not overwhelmed. Examples of things you could do, not things to copy. It's an original thing where you're going to need a bunch of a thing set up like this. So you need to understand the whole draw all calls, draw a fish, draw one fish, and so on. Okay, as long as you understand this higher level, lower level function, you'll be fine. I also strongly agree with the way they've laid this code out. We have the we have the full sequential, like the start function calls at the beginning. We have the draw all function definitions first, and then below that, we have the draw one of the lower level functions after that. It literally is in the code, higher level and lower level, because that's how you would build the function and keep building up, sort of thing. Okay, so that's actually it for 8. Bubble 8 is just understanding the setup. All right, so the first one we're going to add to is the bubbles. Let's look at the high level function, draw all bubbles, is on line 34, draw all bubbles, and it picks a random location with the full screen range, and then it calls draw bubble, draw all bubbles calls draw bubble, and every time draw bubble is called, it sends a random number as the parameter, or sends a random value between 1 and 5 inclusive to the draw bubble function, the draw one bubble function, which is down on 112. And the draw one bubble function receives a parameter named size, and the way it uses size is for the dot size. But before that, it sets the color to a bright blue shade, but with only 20% opacity, and that's how you can see through it if you can find it. There, that tiny one right there. When we have a bunch of them, which is what we're about to do, you'll be able to see them better. So how are we going to draw a bunch of them? Well, we're going to take whatever draws one of them, which is the draw all bubble function that works fine, and we are going to loop it a bunch of times. So you need to go to the control toolbox and bring in a for loop. It's our only loop. Into the draw all bubbles function, and then move what we have inside of it. So instead of just moving to a random number or a random spot and calling the function, we can do all of that 50 times. Is that what it says? Or 200 times? There you go. There are some bubbles. All right, I'll give you another second with it. Okay, so that's it for bubbles. Let's go on to 10. All right. Bubble 10. We are going to take a look at the draw fish and draw all fish. There are a few interesting things here specific to the draw all fish and draw one fish. Okay, draw all fish looks the same. It's actually the same that we had before from last time, which the draw one fish is the same that we had before, which is down on line 91. So this is the same as last time where we had draw fish. It is expecting one parameter that's used for size, and then a parameter for red, green, and blue each, so that we can send it a color. When this is received, it applies size to the things we're familiar with before. Dot size, move forward, pen width, and then all of the move forward things. And let me see, make sure we do. Okay. So what do we need? Well, we need a big loop that calls this a bunch of times. So up here at the draw all fish, we need to add a loop. Okay, draw all fish is on line 28. We need to bring out a for loop. We're going to drag both those things in there and do this. How many times I say, like 15 or 20, 15 fish. There we go, 15 fish. Now, this isn't critical to meeting the minimum requirements, but if you are interested in creative expression, projects, what have you, some things to note are in the draw fish function, it moves to a random location, but it doesn't move to a completely full screen random. So the X 0 to 320 means that our random move to can happen anywhere left or right. But our random for the Y value is 0 to 300, which means the Y randomness will end up somewhere between the top edge, which is 0, and 300 down from the top. So all of our fish will be in this area, which is a large range, but none of the fish will ever show up at the bottom because our range for Y is limited to 300. The other thing that is neat about this is that the random color, well, first we're sending it a random size, which is between 5 and 20, used for all of those different things, not just the size of the dot, the pen size, the sides of the triangle, the fish, and so on. We are sending random numbers for the amount of red, the amount of green, and a hard-coded value for green. Looking at this triplet, the first one is the redness. Its random value is between 200 and 255. yes, it's a random number, but it's a very narrow range and it's a very high range, which means this triplet color is going to be something that is in the red area, red, orange, yellow, pink type of thing. Then we get a random number for green between 100 and 150, which is a medium amount. And we get a hard-coded blue of 120. Now, a couple things. This is how you're getting slightly different shades each time, but not completely different shades each time. We know it's going to be a strong red color, but whenever you have a color that's really strong in one of them, the other two affect the brightness. Okay, that's an important concept. The other two affect the brightness when it's a primarily one of the three colors. And having a slight randomness for the green that is somewhere around the randomness for the blue will keep it in the sort of medium shades of reddish. Okay, finding the exact color that you want is, like I said, it's a good party trick. It's not necessarily necessary for this. Okay, if you're a draw all fish works, where you're doing 15 fish, and actually the only thing you need to do for this bubble was to drag out a loop and put the stuff in there. We didn't make any other changes, but hopefully you learned something. Bubble 11. All right, so we are now going to give the same multiple treatment to C stars. And so if we look at C star, the low level function, let's take a look at the draw C star, draw one C star. Okay, draw C star down on line 57 is expecting a parameter, which gets applied to the word size. And it's used here. It's used for all of the move forwards. Now, I think this is the one where okay. So inside of the low level function, the draw C star function, we have the same thing repeated. Okay, all of the lines of the C star are move forward the same amount, whatever number we send it, and turn right 144 degrees, which will make our star. Anytime you see the same thing exactly repeated, probably a good time for a loop. Although, depending, it could be a good time for a function. So instead of having 5 of the move forward, turn rights, we can have 2 of them done 5 times. And then get rid of the other 4. And that should work. It should look identical to the way it does before. Now, if you recall, the change that we made to this the last time was that in order for it to look right, this particular C star function, in order for it to look right, we had to make the pen width scale with size. And originally, it was the C stars were 60 on a side and the pen width with 20. So if you recall, it was a ratio of 3 to 1. We always want the pen to be a third of whatever the length is. Even though those are sort of unrelated measurements, it still works out scale-wise. You don't need to change that, but I think it's definitely better. Okay, so we've solved our low-level function, draw C star, which, to be fair, it worked before. And I've sort of mixed feelings about going back and changing things that work for small things. It's certainly useful later. It's called refactoring, essentially. But for us, it's we're just practicing. Okay, so the next thing we have to do is go to the higher level function, draw all C stars, which is on line 22. And we want to draw 5 of them. let's say how many, yeah, 5 C stars according to them. And so we need the same thing as before. We need a loop to go inside of the draw all C stars function and drag our little commands in there. And 5 seems to be enough. Let's see what happens. There we go, 5 C stars. And it has the same, the corresponding random situation as the fish, except this time the range of Y values is between 360 and 450, which means it will never be above 360. Y equals 360 is like right there. So the C stars will never start above that horizontal dotted line because of this limited range of random locations, which I think contextually is appropriate. Give you another minute with this, since all you have to do is make your code look like my code. All right, bubble 12. Okay, bubble 12. We have 2 different things to do to the seagrass. We have to go to the lower level function and change a couple of things. Okay, so if we go to the lower level draw, well, it's hard to tell when there's only one, but we have already written, if you go to the draw seagrass function, which is on line 74, we've written it so that it can receive a parameter that changes the size of the arcs. Okay, whatever number we send it, this is from last time, whatever number we send it will represent the size of these arcs, higher number, bigger. But we want an ability to change the number of left rights. Right now, every single time it takes a small left turn, 30-degree left turn of whatever size, and then it goes right, left, right, left, right, left, exactly 3 times. We want seagrass that can be different numbers of left rights and change the size of those left rights. So the way we're going to do that is we're going to add a parameter. Anything you want customizable, you need to make a parameter for. What do we want to customize? They're using the word num waves, which I'm fine with. And where are we going to use that? Well, we're going to use that as the number of times to loop. We want to loop through the left rights num waves number of times. So whatever number we send as the second parameter will be applied to the loop. This is essentially a local variable. Parameters in general are local variables. We haven't talked about variables yet, true. But this is how we're doing it. Because we're going to send it a number as a second parameter, we can use it as any number. In this case, we're using it as the number of times that we loop. So let's go up to the high level function, which is called draw all seagrass on line 15. And right now we're only sending it one parameter, one argument, but sending one value for the first parameter, which is radius, the size of the arcs. But we need to send it two numbers. And this number is going to be how many left rights. If we did one with 10, it would be 10 left rights. If we did one with 2, it would be 2 left rights. Okay, but we don't want an exact number of left rights. We want a random number of left rights, and we need to give it a useful range. The original range was 3. I can't imagine wanting one that had less than 2 left rights. And this is 10, but that's also kind of a small radius. Let's see, maybe 8. These sort of fine-tuning things for the sake of graphic design, I'm not terribly concerned about. Okay. Well, yeah, we'll see it when we get to the next one, which is loops. Where they even have a typo in the or not a typo, but a misclick. And modify draw, it's called 2-param version of seagrass. Yeah, so that's it for bubble 12. And the last stage for bubble 13 is the, wait, no, is there one more? Oh yeah, there's still, so it's not the last one. Okay, so we have a seagrass function that has different sizes of arcs and different number of arcs. There's also a neat, they do essentially the same thing as the color variation with the fish. The draw one seagrass, we don't send it a random number when we call it like we did with draw fish. This works also. Every time it's called, it picks a new random number for color, which is fine. Either way works. But here, the random range is only for green. Both red and blue are zeroed out. And this medium range of green will give us a medium brightness green color. But every time it's called, it will be a slightly different green color, which is what we want. So we need to, in order to do a bunch of this seagrass, we need to go up to draw all seagrass, which is on line 15. And we need to loop. Okay, we already know the move to works because it moves to the bottom edge somewhere left to right. We know it turns due north in order for the function to work. And then our two random values, one for the size of the radius and the other for the number of left rights. We just need to do all of it 50 times. There you go, seagrass. All right. So again, the only thing we did was drag in the loop and put the 3 blocks inside of it. Okay, let's go on to 14, which is kind of the last one, except for a do whatever you want one. Okie dokie. All right. Last one, draw sunbeams. Okay. The sunbeams have an interesting situation. Let's go look at the draw one sunbeam function, the lower level function, which is the last one on line 120. The draw sunbeam function receives a parameter named size, which is used to apply to the move forwardness. It is the length of the sunbeam. Okay, pen width is given a value between 1 and 15 every time it's called, and it's given white as the color, but with 10% opacity. Okay, white is 255, 255, 255. And if you give it a fourth parameter, it is the opacity, in this case 10%. Move forward, and they do the pen down, do a thing, pen up, which is fine. Okay, that's how you make one sunbeam. Let's look at the draw all sunbeams, which is on 48. The first thing you'll notice that's different is the move to the X value range is somewhere between -50 and 320. Well, why is it between -50 and 320? Okay, we know the left side of our screen is X equals 0. The right side is X equals 320. X equals -50 is 50 more pixels to the left. The reason why you need that is because the general shape of the sunbeams comes in from the top left. And if we had this range set at 0, the turtle would never jump left of here, which means all of the sunbeams that we will have eventually will be in this area, and there wouldn't be anything here. The way we solve that is give it the opportunity to jump even farther to the left so that there can be some sunbeams in that area. That's why that's like that. And then turn 2 random between 165 and 175 means they're all going to be going almost straight down, but with a slight variation, which is a interesting effect. And then we call the function sending it somewhere between 100 and 400 as the length. All we need to do here is draw a bunch of them. So we're going to get a loop, drag everything that we already have in there, and to say how many we want. 100 sunbeams, so we'll do 100 of them. And there you go. Draw stuff. What if we did? Okay, so that is the extent of draw all sunbeams. I'll leave it there for a second so you can look at it. Again, all we did was put everything in a loop. And I kind of like how the sea star, you don't have to do this next thing. The sea stars are in front of the seagrass, and that's because seagrass is called first. It draws front to back. But what if we did draw sea stars and then seagrass and then sea stars again? Some of them would be behind. I think that looks cool. You don't have to do that though. Okay. And which is the one I wanted to show? Draw all sunbeams. If we set, instead of having -50 as our XY range, you see that none of the, well, I guess it's not the worst. I recall it being a much more dramatic effect. But you can tell that there's no sunbeams over there, and that's why we get the -50. And that's another thing. The computer will keep track of what's going on outside of the canvas, outside of the screen. You could have stuff like come off the screen at the bottom, jump to the top, and then come on the screen at the top, keeping track of it the whole time. That's how it does it. Okay, and that's it for 14. Bubble 15 is an extend your learning situation. And all you need to do is change something. Change something noticeable. You can add, you can change colors, like change the background, add a different creature. Something that makes it clear you change things and change things different than your neighbors. And that's funny. I know Baker. Yeah. So go ahead and do that. And let's talk about the checks for understanding. You can come back to, if you're keeping up, I would say come back to 15 and pay attention for the checks for understanding. And all right, checks for understanding, bubble 16. See some more AP practice, identify the abstraction. This is just a multiple choice, but your job here is to identify the example of abstraction that you developed, or that is to say, that is a student developed abstraction, which basically just means it can't be, and you could see the do not award a point if any one of the following is true. And it says the response is an existing abstraction, such as variables, existing control structures, event handlers, and APIs, meaning you can't count something App Lab made as your abstraction. Okay. And yeah, so there's that. Take a second to think about that and essentially repeat what I said about explaining why it's that. Okay, bubble 17. All right, so there are going to be questions on the AP exam like this one. And I think they're one of the harder style of questions. Out of 70, I think 70 questions, there might be a handful, like 5 or 6, maybe more, where they give you a chunk of code and say either which shape is the, what does it look like at the end of the code? Or in this case, even harder, which line needs to be deleted in order for it to work? Okay. This requires a relatively high understanding of the concept. Worst case scenario, you can get out a pencil and paper and sort of work through what it's trying to do. But, just sort of talking through it, starts out with a function call. Okay, we have 2 function definitions. Draw 8 squares, which is just the loop of 8 draw squares and some setup movements, which calls draw square, expecting a parameter, and the square is just 4 sides and 4 turns. So this seems like it works. Look in this area and see if you can figure out which line needs to be deleted in order to make this shape. Just work through and explain what's happening. I'll give you a hint, you don't even really need to look at the lower level function. Just trust that it works. Okay, bubble 18, looping in functions. Breaking a problem down, you encounter elements you want to use repeated in your code. Sometimes it's appropriate to write a function, others to write a loop. There's no hard and fast rule for which is better, but what do you think? What circumstances lead you to writing a function versus a loop? Okay, have we written functions and loops? And you've seen how they work. You can essentially think about how we've used functions, which we used them the last couple lessons, including today, and how we used loops, which we just did today. But what sorts of things did we use for looping, and what sort of things do we use for functions? Okay. Using a top-down approach, how would you create a program to draw a white snowflake on a blue background that uses random numbers so the snowflake would be unique every time it runs the code? You don't need to write the entire code for it, but you do need to describe what needs to happen. Okay, where you would loop and where you'd use random numbers. All right. Any questions about this stuff? Remember, make your code look like mine, you get an A or a B.